Now for transitivity. Transitivity for the order. So you've seen several transitivity results, like transitivity for equality. Transitivity always tends to involve three things and a relation. So first to second, second to third implies first to third. So this kind of relationship. You've seen transitivity for inclusion, first to second, second to third, therefore first to third. Certain relations are not transitive, as you saw in this cartoon, that membership is not transitive. You can have a first thing being a member of a second and the second being a member of the third. The first will not necessarily be a member of the third. So transitivity is sometimes true and sometimes not for different objects and relations between those objects. It turns out that for natural numbers and the relation of their ordering, you do have transitivity. And this is something that we have to prove by induction. So here's my theorem statement, theorem 100.1. So let's assume we have three natural numbers, and then assume this, and then prove this. No, scratch that. That's actually absolutely not what we're going to do. But that's what you would think, right? That we're going to assume this, and then prove this. But no, that's not how induction works. So we need to pick the variable that we're going to do induction on. Here, there are quite a few different, there are three natural number variables showing up, so there are quite a few different ways to set up the induction. So when we say we will prove by induction that, let me move this down a little bit. So here are a few different ways we can do things. So we could fix n and m, or how about this? We could fix m and k, assume m and k are natural numbers, and then not say anything about n, and then instead do our induction on n. So prove by induction that for all n is a natural number implies, and then the thing that we want to prove here. And put this in some nice brackets. So this is one way to go. We could fix m and k and then do induction on n. So then our base case would have 0 in place of n. It would have, our induction hypothesis would be this itself, and then we try to prove this with next to n in place of n. Alternatively, we could actually fix n and k, leave m out of the picture initially, and then do our induction on m here. So m here, m here. Then m is the variable that we're doing induction on. Then m would get replaced by 0 for the base case, and m would be the thing that gets, so this would still be the induction hypothesis, but then we would replace m by next m. I'm trying to pronounce it clearly enough that you can hear the difference between n and m. Okay, that's another approach. Another approach we could take is fix n and m, and then actually do your induction on k. So then k gets replaced by 0 for the base case, and k gets all the other replacements. Yet another approach would be not to even fix these, and then instead stick them in the thing that's playing the role of phi. So put it kind of here, and put this in yellow. Like this. Then this whole package would be phi rather than just this part. And this would, sometimes this is actually a useful strategy. So still do induction on k, but make this entire thing in yellow be the thing that you're doing induction on. So then the one advantage this would give you is that when you go to do your induction step, you will have a very powerful induction hypothesis. You'll get to assume this whole giant thing with the for all, which is more powerful than just having a fixed n and m at the beginning where you just have something working for those particular n and m. Sometimes this is needed in proofs by induction. Sometimes you need this technique of making the thing that you're proving by induction include more of the variables under universal quantifier so that you end up with a strong induction hypothesis that you can use. But this is not one of those times. It turns out that in this particular case, this is sufficient. So all we need is this as our phi. And as far as which variable to do induction on, you saw we have three choices, n, m, or k. It turns out k is one that works. I have a vague memory of trying the other ones when I was writing this part of the notes, and I couldn't get it to work. K was the one that ended up working. So often, if you have a lot of different choices of variables to do induction on, sometimes just trying things and seeing which one ends up working is the way to go. So that's why I ended up saying, let's do induction on k. So I'm just adding a comment here. Our phi here is n less than m, and m less than x implies n less than x. And I'm just bringing in this variable x for no reason other than that it is the variable that shows up getting replaced by various things in the statement of mathematical induction. Okay, so remember that throughout this proof, n and m have been fixed. They are arbitrary natural numbers fixed throughout the proof. Now that our phi is clear, there's no doubt as to what our base case must be and what our induction step must be. So I'm just going to duplicate this. Well, let me be a little bit more careful about the induction step. But for the base case, I'll just duplicate it and replace the x by 0. And for the induction step, it'll start like this. Well, hang on. This is not a good way to write my base case. It's true that the base case is the requirement to prove this, but if I just say this as a sentence, then it looks like I'm asserting it. I'm actually trying to say that it's our goal, so we must prove this. So be careful to not do what I just did. Don't just write down an assertion thinking that the reader will understand that you're not saying you've already proven this, you're saying this is what you want to prove. You need to write more to make it clear why suddenly this assertion is being stated. Okay, now for the induction step, suppose n is a natural number, and assume the induction hypothesis. So the induction hypothesis, that's where I can finally duplicate this. It's this, but instead of x here, we have k. K is the variable that I'm doing induction on. So this is not a n, sorry. Then this should also be a k. Right, this is what I'm trying to prove by induction. So my phi of the moment here in my application of Theorem 94, my phi of the moment is what's written here. My n of the moment, the thing playing the role of n for me, is not really the variable n. No, it's the variable k. So that's why I'm talking about k here. Okay, so there's my induction hypothesis. Assume this. Then what must we prove? We must prove that, and then basically this again, but next k instead of k. So next k's go here. Make some space. So, okay, my induction step is set up, my base case is set up. Let me actually do the base case. I haven't done that yet. So let's see, I get to assume this side of the implication, I have to prove this side. But the left side already looks ridiculous. It involves assuming that m is less than 0. And we've seen the problem with that, right? 0 is the empty set, less than is actually membership. This can never happen. Nothing is less than 0. Actually, I feel like that's sort of a fundamental fact about 0 that should be listed here, but I didn't put it here. So I think I really should have listed that there, that nothing is less than 0. Although it's pretty quick, you just say, you know, nothing can be in the empty set. Still, I think it should be there. So this is true. The implication is vacuously true because the hypothesis can never be true. That's because m less than 0, m in the empty set is false. Okay, there. Base case is out of the way. And often you will see when in proofs by induction that the base case is easier and the induction step is harder. But sometimes it's the other way around. There are proofs by induction where it's the base case that's hard and the induction step that's easy. All right, now I need to prove this implication, so let me assume the left side. And usually, instead of this symbol, I'd rather just write and when I'm writing a sentence like assume. Okay, so now my goal is to prove n is less than next k. How in the world am I going to do that? So again, when you're ever stuck in an induction step, look to your induction hypothesis and think, how can I use this? So here's our induction hypothesis. It takes the form of an implication. If we want to use this, we must somehow put ourselves in a position where the hypothesis of this implication is true. So we want to put ourselves in a position where n is less than m and m is less than k. Well, we do have one of those two, n is less than m, but we do not necessarily have m is less than k. Actually, this is a familiar situation, right? You've got sort of k sitting somewhere. Next k is like the dot that comes after it. I usually imagine that natural numbers are like a bunch of dots next to each other. And then there are some other dots, possibly, and maybe a whole bunch of dots, and then the 0 dot at the very end, over there. And what we know about m in relation to k is that m is to the left of here, strictly to the left, so m is somewhere back there. So m could actually be k, or it could be further to the left of k. I want m to be further to the left in order to use the induction hypothesis. And so a case split here will be useful, where I focus on two cases, the one where m is k and the one where m is to the left. So my case split will be driven by m less than or equal to k, which actually is something I have because that's what this says. So now I know what to say next. I'll point out that m is less than or equal to k. For the millionth time, that's us using theorem 96.2. And now we're justified in the following case split. Case 1, this is the case where the induction hypothesis becomes useful, m is less than k. Case 2, which probably the induction hypothesis will not be useful, but maybe we can figure it out anyway, m equals k. Okay, let's look at case 1. So remember, the goal is to reach n less than next k. But case 1 says, basically gives us n less than k. So let's see, by the induction hypothesis, since n is less than m, we have that there, and m is less than k, that's the case assumption, we have n is less than k. Now, Yeah, so our goal is proving n is less than next k. How do I go from n less than k to n less than next k? Here's something that I've often heard students do at this stage of this proof. I've seen it done so many times that I now remember it. They will go, well, n is less than k, and k is less than next k, right? That's because of part 1 here. Things are always less than their own next. So, therefore, n is less than next k. Does that argument work? Do you see what's wrong with this argument? So, here's what's wrong. That argument uses transitivity, right? It's using this principle that if one thing is less than another, and that's less than a third thing, the first is less than the third. But that's exactly what we're trying to prove. That is what we are after here. So definitely we cannot use this fact. So what do we do then? How do we go from n is less than k to n is less than next k? Well, let's break down our goal a little bit. N less than next k, do you see this less than with a next to it? Mush these together. What we're really trying to prove is n is less than or equal to k, right? That's an or statement, and we can prove either side of that or in order to get victory here. So this is what inspires the next step. Therefore, since we have n is less than k or n is equal to k, right? So n is less than or equal to k, so n is less than next k. Using, for the 1,000,001st time, this property. So that's it for case 1. We got what we wanted. On to case 2. Let's clean this up a bit. On to case 2. So when things are equal to other things and they collapse together like this, then what I like to do is rewrite my goal. So our goal becomes, let's see, so the ultimate goal, I guess, here was to prove this implication, and we already made this assumption of the hypothesis of the implication. So this was actually the goal currently, so that goal becomes n is less than next m, since it was k here, and now the k has been replaced by m. So can we prove this, that n is less than next m? Well, we have n is less than m, right? So n is the same trick that we pulled up here, it's just now with n and m rather than m and k, right? So n is less than m, or n equals m. So that's what it means for n to be less than or equal to m. So n is less than next m, which is what our goal became in the situation where m equals k. So that's both cases. The induction step is complete, so the induction is complete, and we have proven transitivity for equality, or for the order on the natural numbers. So specifically, we've proven part 1 here, but it's pretty easy actually to prove the other parts once you have part 1. The other parts just stick a less than or equal to in some positions. So if you put a less than or equal to here or here, you get the same conclusion. If you make them both less than or equal to, then of course you can have equality across the board, and then this has to become a less than or equal to. So there's no additional induction needed to prove these. It's pretty much just case splitting, and it's kind of boring, and that's why I'm leaving it out. Let me give you a quick verbal example, just speaking it out, talking it out. To prove number 2, assume n is less than or equal to m and m is less than k. No induction, just basically assume these, and then try to prove n is less than k. Well, there are 2 cases. Either n is less than m, in which case it reduces to this, and you can use the previous part to conclude n is less than k, or n might be equal to m, in which case this reads actually n is less than k if you just replace the m by n, and then that's the desired conclusion. So stuff like that. Kind of boring. So no induction involved here. This has the induction and did all of the work. All right, so this is quite a great moment in the study of the natural numbers when you're doing this. I think it feels really good to get past theorem 100. It's quite a milestone because transitivity is just something that you constantly want to use, and it's not available until you're doing stuff that comes after theorem 100. So it's just great when it becomes available. Another milestone, I would say, is theorem 104 coming up soon, trichotomy. That's another one that you constantly want to use, and then once you have it established, then you have sort of more of a complete toolkit. Theorem 101, that one is your homework problem to prove that. That one's pretty interesting. So you may have actually noticed when we were proving theorem 100.1, you may have noticed that we never really used the fact that n and m are natural numbers anywhere in the proof. Like, that never actually came up. It never mattered that we made this assumption. That's because we were doing an induction on k, and throughout, k was assumed to be a natural number. So it seems all of this stuff worked, and would have worked even if we did not assume n and m are natural numbers. N and m, let me put it this way, in our work, we don't use n and m are natural numbers, but we do use inequalities where n or m sit on the left side. And that makes them sort of elements of natural numbers, since the less than relation is actually a membership relation. So that actually does make them natural numbers. And this is pretty much what you're going to prove here, that if you have a natural number and then you have an inequality where something sits on the left side, then that something must be a natural number. If you replace this inequality by a membership symbol, which is, after all, what it's defined to be, right? It's defined to be just a fancy way of writing a membership symbol. Then you can see what this is saying. It's saying anytime you have a natural number, its elements are also natural numbers. That's not really something that's fundamental to, the idea of counting or anything like that. That's just a quirk of the set theoretic way we've constructed the numbers. Okay, I think that's all for today. We'll have one more lecture wrapping up this section, and then next week we can get started with recursion and hopefully quickly define addition finally after that.